Hello, I'm Jonathan Ehret, and I'm going to present today our research regarding speech source directivity for embodied conversational agents. We performed this research in a joint effort of the Institute of Hearing Technology and Acoustics and the Virtual Reality Group of the Visual Computing Institute, both at RWTH Aachen University. So I present this work also on behalf of Lukas Asböck, Andrea Bönsch, Janina Fels, and Thorsten Kuhn. To allow you to focus more on the talk's content instead of me, I'll fade my video out for the next slides and return for the conclusion. And I'm very sorry for the background noise, but the fan of my laptop is unfortunately quite noisy. Let me first of all quickly introduce the concept of embodied conversational agents, which get more and more attention in the virtual reality community. Those are computer-controlled visual representations, in our case of humans, which are embedded into a virtual environment. Furthermore, they communicate using natural language, so speech, but due to their embodiment, for example, co-verbal gestures. Here I brought 3 examples of ECAs. First, an ECA which is used as a coach. The advantage here is that the coach can use his body in addition to the speech to show what exercise the user should do or where and how the users are performing exercises wrongly. Next is a negotiation agent helping to train negotiation in a safe environment, which is controlled in a Wizard of Oz paradigm. That means that an actual human controls this ECA in the background. And it negotiates with the participant over these items you can see there on the table. And as a last example, the Breaking Bad behavior system, which can be used to train teachers. Therefore, teachers verbally interact with students while being immersed in this virtual environment. To then train classroom management skills they are confronted with and have to handle disruptive behavior. So what all of these have in common is that they also use natural speech as one modality, which I will be talking more about in the remainder of the talk. So when simulating speaking agents, we will have to consider how they radiate speech sound into space. Most virtual speakers in VR or also in games just radiate the sound into all directions equally, so omnidirectionally. This can be improved by using a directivity filter for the speech sound source that, for example, muffles the speech sound when standing behind the speaker. And this can even be further improved when this filter is adapted based on the current articulation of the agent, so phoneme-based. That's what we call the dynamic directivity here. So before introducing our studies, I will first quickly introduce what directivity filters we used. One approach to generating these filters is measuring the directivity of a sound source, here exemplaric for a clarinet. We use directivities of human singers measured by the Institute of Hearing Technology and Acoustics here at RWTH Aachen University. This gave us one directional filter averaged over very different vocal contents, so different vowels and consonants. However, this approach has limitations in the measurable spectra and the resolution, and is rather expensive, as you can already see here by the apparatus used. So we used this method only for our static directivity condition. Static in our case means that the directivity filter itself is constant over time, but it is still moved with the movement of the head of the agent. So only the filter is constant, not how we apply it to the sound source. So the next step was to adapt the directivity based on the content of the speech. That's why we needed more directivities basically for each different phoneme produced during speech. That is why we went from measuring to simulating the directivity for different formations of the vocal tract using a boundary element method. Following the results of Mark Freixes and colleagues, we could simplify the vocal tract, which you can see here on the top, to a radial symmetric tube, which made our simulations easier. This tube was then embedded into a head model for the boundary element method simulation. We also teamed up with some linguists from the Human Technology Center of the RWTH Aachen University and used this chart of the International Phonetic Alphabet, IPA, to decide on phonemes that would have the strongest difference in the formation of the vocal tract, which we wanted to simulate directivities for. Here you can see the IPA vowel chart with the horizontal dimension being the production position within the mouth, from front to the back, and the vertical dimension showing the opening of the mouth. The phonemes in orange circles were the vowels we decided on for simulation, and it turned out that the horizontal dimension did not play a great role, so E and O produced very similar results. So we ignored O for the studies we performed. Here you can see the differences of the filters, so the thick blue line in the middle is the mean, averaged over all directivities and all directions. The dark blue shaded area shows the standard deviation between the vowels, which only becomes noticeable above 4 kHz. And the mid blue shaded area shows the standard deviation interval between different directions, which shows that this is well noticeable. And that can also be seen with the visualization of the directivity for the vowel A here on the right. Here red is an amplitude of 1, and you can see that the deviation from the unit sphere becomes stronger the higher the frequencies get. So for the direct comparison between dynamic and static directivity, we did not use the measured static directivity from before, but we used the mean of the filters of the individual phonemes directivities to not skew our comparison. Here I brought 3 examples of these directivities with an agent speaking words featuring vowels from the entire IPA vowel chart while turning. First without directionality, so omnidirectional. That sounds like this.
Beat, bit, bait, bat, bat.
Then using a static directivity.
Beat, bit, bait, bat, bat.
And lastly, one that uses dynamic phoneme-dependent directivity. Here we use the filters I described before and switch between those based on what phoneme the agent is about to produce. Therefore, we had to map different phonemes to the same directivity filter due to the already mentioned similarity between those. And therefore, we only had to simulate 3 and use 3 in the also in the simulation here. Then.
Beat, bit, bait, bat, bat, boot, put.
So let me briefly introduce the 3 studies we performed. First, we did a study with an interaction where participants had to collect items for an agent who read orders for items from a screen to feature a lot of back and forth rotation to showcase the differences of the oralization. Here we compared only measured static directivity and omnidirectional sound. Then we conducted a second study, now also incorporating dynamic directivity, where we had an agent act as a tour guide, both indoors and outdoors, giving a 90-second speech about the place. Participants were able to switch between the oralizations during the speech and had to decide which one they preferred and how natural each of those sounded. And then in the third study, also comparing all 3 oralizations, participants had to say which 2 oralizations were the same in an ABX comparison, with the agent giving the same words combination you heard before in the short directivity clips. During the speech, the agents were rotating and participants could start and stop each agent as often as they liked. So here's a short video of this first study we did. Please excuse the background noise that was not as audible during the study due to the cave door being closed. And here using a dynamic crosstalk cancellation actually being computed for the person wearing the glasses, so not for the camera position.
This order for customer L34 requires 17 items. At first we need 2 mobile phones.
Which size do they have?
They are in the smallest kind of box.
In which shelf do I have to look?
There should be plenty of these boxes in shelf 5. Thank you.
How many more are missing?
Please find the one remaining package.
Unfortunately, no difference in the perceived realism could be shown, potentially due to the fact that the agent did not speak that much and participants focused more on the task than on the speaker. Furthermore, we also measured perceived social presence, so the feeling of being together and interacting with an actual person. This can be done by objective measures, like for example proxemics, so whether participants respect the personal space of the virtual agent, which they would not do for a lifeless object. That is also the reason why we designed the stock room to be rather narrow, to force participants to pass often close by the agent and see whether there is a measurable difference between the distance kept for omnidirectional and static directivity. Additionally, we also used a questionnaire-based measure, namely the social presence survey by Bailson and colleagues. However, no significant differences could be found for both of these measures. Especially the questionnaire-based values, so the SPS, showed a lot of variance, probably due to the fact that it is hard to rate this concept after such short and not very social interactions. Therefore, we focused more on naturalness in the following studies. So skipping the second study for now, here are the results for the third study, where participants had to rate in an ABX comparison which two oralizations are the same. The results show in the left two bars that participants were, not surprisingly, well able to distinguish omnidirectional sound radiation from both directional cases. However, in the ABX comparison between the static and dynamic directivity, we found no significant differences from chance using a binomial test, and therefore we have to conclude that those were not distinguishable, at least in our given setting. Here is a short clip of the second study, in this case in the outdoor environment. You can see that participants were able to switch between the oralizations by clicking buttons on the interaction device. That's shown here by crosses, and you can see which variant is playing on the stand next to the agent and also on the top.
The Somerset House was initially built to house governmental offices. Today, it is an arts and cultural centre, housing concerts, exhibitions, films, and workshops year-round. The architecture of the building reflects a neoclassical style. This style is all about symmetry, evident in the repetition of form and similarity of lines. We see even-spaced windows, repeating brick facade patterns, etc.
And after listening to the entire 90 seconds talk, they had to rate each variant and pick their preferred one using this questionnaire here, which was then embedded directly into VR. When looking now how natural each of the oralizations in the study 2 was perceived, we surprisingly were not able to find any differences. Here the plot shows the results both for indoors and outdoors, because another hypothesis of our study was that this might be different between a free field outdoor situation and an indoor scenario where we simulated the reflections at the walls, which however also was not the case. When, however, taking a closer look at the data, we observed that several participants consistently preferred either one of the directional oralizations or the omnidirectional one. So this plot here shows the number of choices for static or dynamic on the x-axis, which does not look normally distributed. We combined here both directional cases due to the indistinguishability observation from before. When then clustering the participants by this observation, and checking again for how natural they rated each oralization, we get significant differences for the non-indifferent participants. This means that while there is no clear preference for either directional or omnidirectional oralizations, participants still preferred the oralization they deemed more natural. So our takeaway messages would be that dynamic directivity, at least in the way we simulated it, might not be needed for speech, since it cannot be distinguished from just using a directivity filter averaged over all human phonemes, even when given full control to switch between those. Secondly, preference for directional or omnidirectional speech sound seems very subjective. This might be partly due to the speech perception, which becomes worse with more realistic rendering due to dampening effects and so on. However, our participants preferred the speech oralization, which they rated as more natural, so striving for higher naturalness seems very worthwhile doing in this context of speech audio. And lastly, social presence, although being a well-established instrument in the ECA community, seems to be an inappropriate measure to find differences for such subtle changes like speech directivity, and we would not advise to use it for these kind of studies. That leaves me only to thank you for your attention on behalf of the entire team, and I would be happy to answer any questions you might have. And if you want to take a closer look at the studies and the results presented here, feel free to have a read into the papers on our website. So, thanks a lot.